Oh,
There you go.
hi.
Should be good now.
Thanks. I finished the proof. Oh,
Oh, you're just hiding in the front.
no, but here, this
Yeah. No,
there are two cameras, I
they'll
think.
probably be
Oh, I see now.
they'll see the highlighted.
Okay. So I'm just gonna use the 4 boards here, so you don't have to switch. So I'm gonna prove one of the theorems that I claimed last time is if kappa is weakly compact, then there exists a diamond lambda sequence for any kappa for any lambda. Okay, true. Yes. Sure. No problem.
Okay, so this is some sort of die, yes.
Mhm.
Does it give you the sorts of things, consequences that diamond would give you?
It depends on what kind of consequences we're talking about.
You sort of say it gives me consequences of this kind, but doesn't give me consequences of that kind. Trying to get an idea. Right?
Yes, that's a good question. I know very little about the applications of such principles in terms of like more interesting consequences. Of course, itself is it's a consequence of yeah no but yeah, that's it's a place where it's not much is known, especially at the inaccessible even if you assume inaccessible diamond, I guess the kind of things you can construct is also limited compared to diamond at LF1. So it's not clear if this is really weaker than the full diamond principle for all lambda. If you can go over, if you fix some lambda, then there are ways to separate such principle and diamond. But then if you insist that for all lambda this is true, then it's not clear. Or at least I have no way of separating them. I don't have a model such that for all lambda this is true, but diamond fail. Yes, if you fix some lambda, I can produce a model such that let's say if lambda is the best function, alpha maps to 2 to the alpha, and that particular sequence, there are models where that's true for this particular diamond, but then the real diamond, the full diamond fails.
And there are various variations of diamond.
Mm-hmm. Uh-huh.
So usually there's a version of here that where designers create their systems. I might ask you whether you have the consequences for ladder systems that you do construct to see if there's any consequences diamond that I know about.
Uh-huh.
Yeah.
What would be a
Aaron shine trees, things like that. So we
yeah, so yeah, it may be useful to construct some strong colorings, but like those combinatorial objects like trees, for example, Aaron tree property,
it's part of it.
yeah.
There are, indeed, there are coloring principles that follow from theory. Simon was wondering, if we give you coloring principles,
I haven't looked into any of that, but it's possible. That's all I can say.
How do I do it?
that's what I was trying.
Right.
Got diamond.
Right. Uh-huh. I have a feeling that this kind of diamond will only give you a very weak form of uniformization. Uniformization. Right. You may have to change the equality in the uniformization by some domination for if you have some kind of diamond, then you would have the failure of that version of uniformization. Exactly. That's a weak form of because uniformization, I guess you want this to happen on a club, right? Whenever you have a ladder system, you want to have on a sequence of functions, that uniformizes on the club or something. It's possible that there are probably versions of uniformization properties that would fail, yes, because this is true. But yeah, it will be interesting to see what exactly. Oh, okay. Any other question? Okay, so I'll prove this. So so the idea is simple. So we just recursively build these functions. What the G delta and pi lambda I like less than delta, delta less than kappa. So at stage delta, we ask if the sequence that we have built so far is good. Okay, so I such that I less than delta is good. AKA, if, okay, actually we should ask if it's bad. So if it's bad, so this means that, AKA, there exists some G in the product up to delta such that on a club, C delta subset of delta, it is true that for all I in C delta, G I is dominated by G restricted to I. So we asked if it's the sequence that we built so far is good. Now, if it's not good, meaning it's bad, then it means that there exists some kind of candidate we're gonna put on the next step. But there's a caveat here. So okay, so if the sequence so far, so G restricted to delta is bad, AKA there exists such a function that dominates everything so far, then pick G delta to be the less than star least witness. Now I have to say something. When delta is of Coff omega, then this doesn't make sense. So we only do something non-trivial if delta is of Coff uncountable. So only do something non-trivial when the cofinality of delta is greater than omega. Okay,
The before versus I said last week.
yes.
So this is 12 pounds is fine, but it's not linear. So what do you mean by least?
I mean minimal.
So that's any.
Yeah, any minimal. Yeah, that's good. So any minimal element would work. Okay, so the construction is done. So we have to verify. The claim is that the sequence, okay, delta in kappa. This is diamond lambda kappa sequence.
So let me just get positive. Correct.
Sure.
Okay, so failure, so you want the G deltas to dominate on the stationary set. So the failure is your G is dominating on the clock. Is that right?
Yes, the G is dominating
Right,
all
so
the
that's,
clock.
that's what it needs to be back. So you've got, so you're choosing a G delta which dominates the previous G's on the clock.
Exactly.
Okay.
Yeah, that's right. Yeah. So if you can find such a thing, then do that. And then if not, then just define G delta to be anything. Okay. So why is this true? Suppose not. Then there exists let's call it F in the global product such that on the club C of kappa, it is true that for any alpha, for any I in C, Gi is dominated by F, restricted to I, right? So, and also we may assume, we may take F to be the least. Yeah, important. Huh? A, yes, A. Okay. Sorry. English is not my first language. Minimum. Okay. I should also write minimal, right? Otherwise, they would think it's minimum element. Satisfying this. Okay, so now we have to apply the weak compactness assumption. Okay, so since kappa is weakly compact, so we can take a model. So M is a kappa model, a transitive kappa model. So I'll explain what this means. This just means that M has size kappa, and M is close on the less than kappa sequences. And we can take M to contain all our favorite things. So in particular, the G. Yeah. But it's already close on the kappa sequences. That's probably. So V kappa is also a subset of M. And also we want the sequence that we want to prove is inside as well. But we can also sneak in the F, right? F is size kappa. Okay, so it contains everything that we like. And it's also close on the less than kappa sequence. We can take such a model. So, and there exists an elementary embedding. Okay, this also means that M is a model of ZFC minus power set. Okay. Oh, okay. Think about that. It's ZFC, whatever. That's the elementary embedding. Right. So we can embed this N to another kappa model. This is another kappa model. And then we want this to have critical point kappa. Okay, so the point is always, let's look at J of G at kappa. Right, so we have already defined a sequence. Now we're trying to stretch it, right? So this is like ultra power. You're stretching it, and then we're looking at the kappa coordinate. It's going to output. I'm going to call this G kappa. So first of all, so A, G kappa is bad for the previous sequence. Now, the reason is, think about how we define these things. If there's a witness that it is bad, then you have to take it. Now, okay, so when you stretch the sequence, you're doing something inside this N. So you need the witness to be a member of this N. But then it is true, right? So what's one particular witness I can produce is J of F intersect, restricted to kappa, which is F. This is in N. And then J of C intersect kappa is C. This is in N. So we have a witness in N such that it is bad. So in particular, G kappa is not defined trivially. Okay, so this is one thing. And the other thing that will immediately give us something bad So the other thing is that we know that F is bad. So F is bad, aka for any I in the club, G I is dominated by F restricted to I. And then because this G sequence and F sequence, they're both in M. So we can apply J to this statement, right? So if you apply J to this statement by elementarity, of J, so apply to this statement, you have for all I in J of C, J of G output I is dominated by J of F restricted to I. But then in particular, kappa is in J of C, right? Because C is a club. C is a club. And then if you apply, J of C intersect kappa is just C. So this is unbounded in kappa. So by closure, kappa has to be in. So this implies that J of G bar kappa, which is G kappa, is dominated by F restricted, just F. But then this is the problem, right? Because G is bad, F is also bad, but F is supposed to be the minimum bad. But now we found something that's even dominated by something that is a minimum bad. So that's a contradiction. Can you repeat? Oh, it cannot be equal because assuming this by elementarity, G kappa is supposed to be dominated by F. Right. So we're applying the statement in N, and then we have shown there's one tricky bit. This is only true in N, and you need to show this is also something that I think should be highlighted is that if this is true in N, then it has to be true in in V as well. But then there's some absoluteness in me. If you're a club in the kappa model, then a club is still a club in V. So if you try to show something that's a little bit more involved, like a bigger ideal, then it may not be it may be the case that when you have a stationary set in N, such that N thinks that it is stationary, but when you go to V, it becomes non-stationary. But then when it comes to club, it's not a problem. When you have a club in N, it's a club anywhere.
I mean, this is a very general thing. I mean, diamonds are false.
Right. Yeah. This. Yeah. So I think the one thing that wouldn't work in the usual diamond situation is is if you insist equality, and then I think of this proof as using some features of like L, because this is, you have a canonical way of picking a counterexample that's different from the usual proof of diamond following from measurable cardinals, for example. In that situation, we just pick any counterexample and then we say whatever works. But here we put in some, something canonical, and it's the very specific statement, the negation of this, that allows us to do that. And I think yours was wondering if we can, last time he asked if we can prove the diamond D version of this statement, which is, instead of saying that G delta is not dominated by F restricted to delta, we say, okay, F restricted to delta is dominated by G delta. And at least it's not clear to me. Well, for this proof, you need the negation to have well-foundedness in something canonical. So we can choose not just any counterexample, but a better counterexample. So if you think about the diamond D version of this, the negation would be something happens on the stationary set, and that's there are some other assumptions that let's say I may be able to add some other assumptions to get it, but just from weakly compact, it's a little bit unclear.
Now, the well-foundedness here, I mean, it's nice to have well-foundedness, but wouldn't this proof work if your well-ordering is simply sort of locally defined, things that in V delta can be ordered by definition in V delta?
Exactly. Yes. That's also true. That's that was actually one of the remarks that I said last time, and very imprecise way about some specific model of set theory where you do have the well ordering that's kind of locally definable, and you can also run a proof like this. I'll mention this a little bit later, but then that kind of that ordering, basically you want some absoluteness. You want the ordering to be absolute between this Kappa model and the outside world, right? The contradiction we get here is that N thinks that we get something that's even less than the minimum one that we already picked in V. But then the point is that whatever N thinks is true in terms of this ordering is also true in V. And then in D, if you have some kind of ordering, well ordering, and if it's absolute between Kappa models and the outside model, and that's going to work as well. I mean, that's going to give you the real time. Okay. Yes. Yeah.
You can't expect that stationary set to that you do along those stationary set. It may not happen. So.
Yes. So yeah. So this in particular, all these deltas would be regular, right? So there's nothing really we can. You can, okay. I want to be precise. You can show such diamond sequence holding on singulars if you have some large cardinals from below, right? So if you have super compact cardinals from below, then you have, and also you don't have that on Coff omega. You just have that on just singulars. It's actually the mysterious singulars where the cofinality, we don't know, but it's but yeah, that's okay. Any other questions? Okay, so another thing, so this is one. Okay, so this is one theorem that I said last time I didn't prove, but it may be interesting to see if we can squeeze in a little bit more, aka proving. Again, it's always proving stronger guessing principles from the minimum compactness. I should say that if you want the guessing set to be slightly larger, there are analogous results. If you assume, let's say, if you assume kappa is pi1, 2 indescribable, then you can get you can replace S to be something in the pi1, 1 ideal. Okay, positive with respect to pi1, 1 ideal, etc., etc. So that's just analogous statements. Okay, so the second theorem that I didn't prove is the following: GCH and this weaker, okay, and this weaker diamond on singulars of Coff greater than omega implies the real diamond. Okay, so yeah. So let's prove this. So basically, the idea is that okay, I should say this is the sequence 2 to the alpha less than kappa, but this is just alpha plus, right? So in order to prove these any diamond principle, it always involves putting pieces together in the right way. In a timely way, right? We want to guess things timely, not like, wait for a while, we can't wait. We really need to just guess things at a specific point. So let's fix these diamond sequence. So I less than delta, I plus. This is delta in singular, kappa greater than omega. So this is a diamond Beth singular kappa greater than omega sequence. So using this, we're trying to cook up a real diamond sequence. So I should say the idea is the following. Let's draw some picture. All right, so we have these local things. Okay, not enough space. Okay, so you have some local, these are alpha and 2 to the alpha, which is alpha plus. And suppose you have a global function, or you have a bunch of local functions. You have a bunch of local functions, but the point is that whenever you give me a global function, there's always a local function such that it's above this global function on the stationary set. So here is the local. Which one is the local function? This. And there's a good way of translating. I suppose I have a set X subset of kappa. What would be a natural translation of this set into a global function in such a product. So a natural translation is the following. If you look at I less than kappa, you look at the index of X intercept I. Now, what does this mean? X, okay, let's let X, I, J, J less than I plus enumerate the power set of I. Right? Because of the cardinal arithmetic assumption, we can always enumerate power set of I in the length of I plus. And then if you'll give me a subset of kappa, a natural association is just to output the index. So suppose we can guess the index set, then of course we can put those sets together to get the diamond sequence, right? If let's say if I guess this function exactly below delta, then obviously if we know all the indices and also I know the enumerations of the power sets of each local function, I can just pick those local sets and take the union, and that's going to recover the X. So that's the idea. Okay, so what? So this is a digression. So we fix. So let's fix a few notations, right? So for each delta in this singular collection of let's assume that these are cardinals. Ordinals, though. The collection of cardinals is a club. So let's fix C delta subset of delta, which is a club of order type cofinality of delta, this singular and greater than omega. So first of all, we fix a club for each singular cardinals there of small order type. And this is important because I'll mention why this is useful. And also, let's look at, for each such delta, let's look at all the bounded functions. So, yes. Right, so, but we are just trying to get diamond on yeah. Yeah, that's indeed a tricky point. Yeah, that's indeed a tricky point. Like what? Yes, for now we don't have to worry about that. So this is the collection of bounded functions of delta. So basically, this is just the collection of H such that it is a function from this club C delta to delta such that the range of H is bounded by delta prime for some delta prime less than delta. Now this is, let's just think, what's the cardinality of this set, right? So if we don't bound the range, the cardinality of this set is large. If we don't bound the range, then the cardinality of this set is supposed to be delta plus, right? Because C delta has order type called delta. So delta to this has to be greater or equal to delta plus, Koenig's lemma. But then the extra wrinkle here is we only consider bounded functions. If we only consider bounded functions, then we're lucky. So this to the power of cofinality of that is so it's just the supremum of delta less than delta, such that this is. But then we have GCH, so this is just delta. So the key point is that this collection of functions is small, and it's only the key point is that we bound the range. And what else do we need? Okay, so let me just, so for any okay, ordinal beta, let me just write f beta to be the bijection between the cardinality of the ordinal and the ordinal. Okay, and I think I am ready to define. Yes, we got the index. Oh, yes. Yes. I'm thinking about which one to change. Maybe H. Okay, I'm gonna erase this. Let's pretend that this doesn't happen. Okay, yeah, nothing. So I can keep using this board. So, okay, so now let's try to. Oh, I should also enumerate, right? So let me write it down again. So x beta I less than beta plus. It's just an enumeration of the power set of beta. Okay, so these are all the data that we need in order to define the diamond. So let's. Okay, so we would define. Actually, we're defining diamond minus. So this just means that at level delta, you're allowed to have delta many candidates instead of just one. But by theorem of Cunin, this is equivalent to diamond.
Who I was wondering, the proof goes, the omega-1 proof goes through in this context as well?
The omega-1 proof.
Well, that diamond is the same as diamond, the counted with diamonds.
Yes.
It does both.
Yeah, and also it goes through if you restrict it to any stationary set. So diamond minus of S is equivalent to diamond of S for any stationary S.
At any time.
Any kappa, yeah. Okay, so at delta in this singular cardinals of uncountable cofinality, the following set A delta is going to be the guessing set. So this is a collection of unions of X beta such that beta is in Y. I'll explain, but I'll just try to make sure that I write things down in the correct way. And I'll put H of beta. And then we are taking Y to be a subset of C delta. And then H is the bounded function. Bounded function of delta. Okay, so first of all, let's look at this set and then compute a cardinality. This is a club of delta of small order type, right? So the order type is just cofinality of delta, which is less than delta. And 2 to the whatever that is going to be small. So, you know, the power set of cofinality of delta is going to be less than delta by the GCH assumption. And then the collection of bounded functions in, you know, this collection, we just described the cardinality of this. This is also a small set. Small set, or not that small, but it has cardinality exactly delta. So this collection would be a collection of sets of cardinality exactly or less or equal to delta, which is good because in order to define a diamond minus sequence, for each level, you need to only allow to have sets. How many sets? You're allowed to have only delta many sets. That's the first non-trivial instance, by the way. If you're allowed to have delta plus, then you might as well just have everything. Okay, so and what are we defining? So we're taking a subset of this club, and then we're looking. So the idea is that this subset is supposed to collecting the indices. That's correct. Right. So it's supposed to collect the indices such that the output of the relative set in the enumeration of the power set of the local set is supposed to be the initial segment of the set we're given, the big X. So okay, should I? Okay, this is it's actually let me just draw a picture and then pretend so let me draw a picture. So locally, right, at delta, we have a C delta, which is, let's be very concrete. So delta, let's say this is of cofinality omega 1. Then we have a club. We have a club such that it is C delta, and the order type of this club is omega 1. And then at each, so each alpha here, we have alpha plus, we have alpha plus, and then beta here, we have beta plus. And then we have some local functions here. So remember, we have some local function G delta, which is supposed to be given by the approximating diamond. So it's telling us, imagine that this is gamma plus. Imagine that this local function is telling us what's the index that you have to, what's the index you have to look for in order to see your the index of the set you're guessing globally. So if G delta of alpha, this is outputting an element in alpha plus. You should think about that as an index. It's telling you that in order to guess that particular subset of the global one, you don't really have to go beyond this index. And this is the same for every coordinate. And and just because the set that we're considering here has small order type, we afford to take all this, any subset of that, because 2 to omega 1 is small. So that's roughly the idea of how this works. I think I'm going to skip the verification of that just because I also wanted to say something about the general methods of proving independence results. So I think I'm going to just leave it here, but the idea is simple. Again, the local functions is telling us how far you have to go in what kind of approximating the indices that we have to look in order to approximate the global one. And
it would be fine with everything was fine. So in order to fix that in the definition, we have to have the bijection between the ordinal and its cardinality.
exactly.
Everything, it's not really the alpha and alpha plus, it's like every alpha has like cardinality.
Exactly. So yeah, so G delta of alpha is outputting ordinal in alpha plus. So you should really think about that as it's basically just outputting some alpha. I mean, it's not alpha, but it's bijectively the same as alpha. And the reason, okay, that's one reason why we need this, because of the fact that we are only considering bounded functions. You imagine that I need to do Fodor's lemma somewhere because because if I can bound these guys, if I can bound this f h, then if it's not a bounded function, then we get into trouble of picking too many sets. But the reason why this is essentially alpha is good, because anything below is less than alpha, and we have a press down function. So sorry, this is very vague, but I just feel that
Let me just ask one, I'm still missing the part.
Yes.
You're dominating the index, the enumerating function.
yes.
What part is giving you the exact guess? That's seems I'm missing that.
Uh-huh. So
You're above the guess.
If you trade in the email.
right. So this particular set is all the potential guesses at level delta.
Yeah.
Right. So here we're trying to use this local guessing function given by the weaker diamond to tell us up to what point the index should we take. And so
that'll give you a place that you don't have to search higher.
yes, exactly.
But your real guess might be lower, and I don't see in the same delta where you're getting it.
Oh, yes, that's where this f is coming in.
Oh, I see.
Right. So f is all the possible bounded functions. So we have to go over all of them. Yeah, it may be, yeah, indeed. Yeah. So you're allowed to go lower, but then you have to do it in a bounded way. Right. If it's unbounded, then there are too many guesses. Okay. I'll try to say something about forcing, but I'll try to make it reasonably understandable. I don't know if I'm able to say all of them, but so I decided to just talk about this rating forcing. I'll give the full definitions, and then I will say usually what kind of properties that is used, what kind of properties are useful in these kind of forcings in analyzing combinatorial principles inside. But I think these are the proofs that the real proofs that I'll give today. So let's just try to define rating forcing. So suppose we have so definition. So let kappa be a measurable cardinal. Then we can define what the usual way that this is witnessed to be a measurable cardinal is by some normal measure. Normal kappa complete on kappa. So this is the usual witness. And now we want to define a magic sequence. A magic sequence is of the following form. So I'm going to call it U bar. So it starts with kappa, which is the critical point of all of these guys. And then it follows by U alpha, alpha less than the length of this magic sequence. So such that U alpha is a kappa complete ultrafilter on V kappa. So you should, it's not necessarily normal in this case. I mean, what does that mean? It's just the ultrafilter on V kappa. V kappa is just a set of size kappa. So we can, we can put ultrafilter on any set of size kappa. And then we also insist that it's kappa complete. That's it. And so this is the definition of magic sequence. But then I'm going to give you a very concrete recipe of how to produce such things, right? So concretely, suppose I have an elementary embedding, right? So given an elementary embedding, such that the critical point is kappa, then of course we can, in the usual way, we can derive a measure, right? So we can derive U0, which is just a collection of X subset of kappa, such that kappa is in J of X. This is just the way of deriving a normal algebra. But then we can continue. Then we ask if U0 is a member of M, then we can derive U1 as the collection of X subset of V kappa. Now we want to, you see why, and if and only if, let's say, kappa concatenated with U0 is in J of X. Now this makes sense because J of V kappa is just V of J kappa. So it is, if U0 is a member of M, it should belong to J of V kappa. So we can keep deriving ultrafilter in this way, right? As long as V0 is inside. Now, what kind of objects this will concentrate on? This is going to concentrate on objects looking like this. You start with the measurable cardinal, and then you follow it up with a measure witnessing the measurable cardinal that you start with. Okay, and then if U1, okay, if U1 happens to be in M, we don't know, right? We don't know if U0, U1 are in M, but then if they happen to be inside, then we can keep going. Okay, so we keep going. So we can define U2 to be the collection of X subset of V kappa, such that kappa concatenate with U0, concatenate with U1 is in J of X, right? Okay, I should just say this. More consistent with my notation there. So we can keep going. And then, so in general, if U restricted to beta is in N, then we can define U beta to be the collection of X subset of V kappa, such that U bar restricted to beta is in J of X. Now, exactly how far you can go depends on how strong the elementary embedding that you start with, right? So if you start with an elementary embedding such that this is very strong, well, when I said it's very strong, it just means that M is very similar to V. So if M is very similar to V in terms of, let's say they agree on very large initial segment, then this process could go on for a long time, right? As long as you have all these magic sequences in M, then you can keep defining the next one. Okay, so what kind of forcing that? This sequence, magic sequence, is used to define the forcing, and I think I should probably remind you of what Prequi forcing is, and then it would be very natural to define this as a generalization of Prequi forcing. So recall. So if we just look at the first measure, right, U0, I'm just gonna call it U. It's a normal kappa complete measure on kappa, then the pre-forcing with respect to u, so let's call it pu, is just the conditions are S A, such that S is the finite increasing sequence of kappa, and U and A is the measure one set in the measure. And also, I guess we want the maximum of S to be less than the minimum of A, right? And then this is like Matthias forcing, but then, well, not quite. This is like Matthias forcing in the countable case, but in the measurable case, you still insist that the first coordinate is finite. This is important. The naive generalization would be, oh, I'm taking S to be all the less than kappa size, but that's indeed a generalization of Matthias forcing. So that would be, that's a different forcing than this. So what are the two operations that allowed us to extend the condition, right? In order to define the forcing, we need to define what's inside and then what's the extension relation. So there are two operations. A is that we can just shrink the measure one set. So if I have SA, this is the condition in the forcing. I can go to a stronger one. This means stronger. S A prime, such that A prime is a subset of A, and A prime is also in U. So I can shrink the measure one set to make it stronger without touching the stem. Or the other operation is that I can enlarge the stem. So SA, I can pick something out of the stem. No, I can pick something out of the measure one set. So S concatenated with alpha, and then I shrink this above this ordinal. And I want alpha to be in A. So basically you have a finite stem and you have some large pool, and then you're allowed to pick from your pool and put it into a finite stem. And then you can, and you're also allowed to shrink the pool to make it smaller. And then the general extension relation is just that you can, if you can get from one condition to the other condition by by performing these operations finitely many steps. So I can shrink, I pull, and then, shrink and then pull. Okay, so so this is the forcing that if you do this forcing, it's going to preserve all cardinals, and it's going to singularize kappa to omega. Think about what S is doing. S is approximating the Kopf omega sequence converging to kappa. Okay, so what? Yes. Yes, yes. So so reinforcing is a generalization of this. So there are a couple of motivations, right? So in this forcing, it singularizes kappa to something of Kopf omega. Now, the first naive question is that, can we singularize kappa to Kopf omega 1, for example? And it turns out that you can. And it turns out that this is the, let's say, rating forcing is a generalization of the Prickly forcing to filters. So what does this mean exactly? So in the Prickly forcing, the right-hand side, you're defining with respect to an ultrafilter. Rating forcing, instead of defining with an ultrafilter, you only define this forcing with a filter. And so our U bar, so U is just a measure sequence. Then the filter that we're looking at is the intersection of U bar. So what does this mean? This just means that X is a subset of V kappa such that X is in U alpha for any alpha less than the length of this measure sequence. It's a filter, it's not an ultra filter. But this is the filter that we're going to define reinforcing out of. Wait, say that again.
Funny things happen when you take the intersection and filter. Actually gives you larger section of the section. So if you intersect two alpha filters, what you end up with is you concentrate on sets which are the union of filters.
Yeah, it's like if you intersect only two, it's like you have ordinals, but then you also have weird objects on the other side. Yeah, so okay, so that's so let me just say that what the elements inside this forcing are, and also I'm gonna say what these two parallel operations are. So elements inside R of U would be the collection of, I've written it down. Okay. So it would be a finite sequence, di, such that I less or equal to k. So this is a finite sequence. Now the top part, okay, so the top part, which is the last guy. Did I say? So dk is supposed to be the pair U and A, such that A, U bar. A is in the intersection of U bar. So this is like, this is very similar to quick forcing. The top part is what we're specifying the measure that measure sequence we're using, and we'll make sure that we have a large set. A is large with respect to the filter. And then what about other things? Other things are the reflections of such objects in V kappa, right? If you have, okay, so what's the other thing? So for I less than kappa, so di is either an ordinal, right? It's either an ordinal, or this is the lowest type. Or if it's not an ordinal, it has to be a pair. Either. Or di is actually a measure sequence. And imagine one set. So AI is in the intersection of UI. So you should think about this A, right? A is a measure one set with respect to this measure sequence, but then also A concentrates on measure sequences. If you use elementarity, right? Think about how elements inside this U bar is generated. They're generated by measure sequences. So A is supposed to concentrate on measure sequences, but they are smaller, right? They reflect down. If you look at the M side, all of these this measure one set is concentrated on is generated by a measure sequence on kappa, but kappa is less than V kappa, J of kappa.
The sequence has like two, then you're talking about principle.
It
concentrates on there's just one signal.
It's so if the magic sequence has type 2, so the first one is concentrating on ordinal. Now the second one is concentrating on magic sequence of length 1. Right. So when you talk about
It's concentrating on the measure sequence of length 1, which is that single.
no, it's so that's the one that's generating. So when you reflect now, it's actually think about when you define the measure. So you say x is in the measure if and only kappa is in J of x. Now kappa is the generic point, right? This is defining.
Oh, so these UIs are on the smaller cardinals?
Yes, exactly. Exactly. UI is on smaller cardinal. It's like a reflection of this. Right. So I should say that for each UI, there's associated a critical point, which is the first coordinate, right? So I'm gonna write it as kappa of UI. And you're exactly right. If I should say that all of these ordinals, associated ordinal, whether it's an ordinal itself or it's a magic sequence, then there's a critical point out there. And I insist that all of these, this is increasing. So what kind of operations are there? So this is the kind of objects that lie in the such forcing. So what kind of operations that are allowed? It's exactly like the pre-grid forcing situation. The direct extension, which is the first type, we're allowed to shrink measure 1 sets. So think about, let's give a very concrete example of so let's say U, A, this is one coordinate, and then we have small u, A, this is a magic sequence is kind of smaller. And then finally we have an alpha, which is an ordinal. Okay, this is the condition. And then I just want to describe what kind of operations are allowed. So the first type of operation is to shrink measure 1 sets. So I can shrink this, and then I can shrink this. And then that's allowed. That gives you a stronger condition. And the other way, is to pull out new elements. So I can either pull out elements from this and put it inside this interval. I always have to make sure that everything inside is above the guy that's preceding it immediately. And I can also pull out guys from A and put it inside this interval. So this is supposed to concentrate on 2 things. I mean, let's say if this has length 2, then guys inside could be ordinals or magic sequence of length 1. But in any case, if I pull out something, the critical point has to be greater than the critical points of all things in before it. So that's the other operation that's allowed. So again, just like in pre-grid forcing, I'm allowed to pull out a point from the measure 1 set, but I'm only allowed to pull out a point such that it's greater than all the finite stems that already exist there. Right? When in pre-grid forcing, when I pull out a point, this point has to be greater than everything in S. And that's the same here. We're pulling out a magic sequence, and we are only able to put it inside this interval, or in between all the previous guys and the next guy. And then the same here. You can also pull out guys from this measure 1 set, and then you cannot put it. Okay, for example, you cannot pull out something and put it in the beginning. That's not allowed. you're only able to do it immediately in the gap before. Okay, so that's so I hope that's kind of reasonable to say that, suggest that this is like a natural generalization of prequick forcing. The point is the following. Let's say if you start with a magic sequence of length 2, and then this is the magic sequence of length 1, then this part is just like prequick forcing, right? So in the end, you produce the omega sequence here, and and then you repeat, and then you look at this part. This part is just like another rating forcing. So it also produces another omega sequence. So
Is there a factorization?
there is a factorization indeed. So that's actually key, because this is not an iteration of any sort. But then in order to analyze compactness principles or diamond, it's important for forcings to have factorization. And you're exactly right. If you have this kind of configuration, if you force below this condition, it's actually equivalent to forcing this part and then times the part above.
But the part above is not new.
It's not. It's a product.
Is it similar to thinking of Matthias forcing the first ball out and around the alpha filter and then diagonalizing that? Is that the second part of it?
Not quite, just because right. So in the first step, if you add the Ramsey ultra filter, it's kind of like if you're adding a magic sequence. But here, the factorization, the first part, it's just a product. The first part is actually a small forcing, right? So if you break this forcing here, this part of the forcing is small. So this part of forcing is large. So this has the flavor of iterative forcing. When you cut it at some initial step, it's a small forcing. It's only after you iterate all the way to a large cardinal, something interesting happens. If you just cut it at some initial step, it's a small forcing. So okay, I should think obviously of no. Okay, so let me say something about the properties of this forcing, which is also reminiscent of Matthias forcing, I guess. So the first property is that this forcing is kappa plus CC, right? Why? Because there's a top part. This part is large, but all the previous parts is small, meaning that there are elements of V kappa. So if we have two conditions that has the same small part, then they're comparable, because this is, this is two sets in the filter that should intersect to be inside the filter as well. So kappa plus CC. But also another thing that is important is that, so RU satisfies the prequick property. So this just means that whenever you have a condition and you have a sigma, which is the language in the forcing, okay, it's something, it's a statement in the forcing language. Then we can, then there is a direct extension. No, I didn't say what this means, such that Q forces sigma or Q forces sigma, the negation of that. This means that the second operation, the first operation, this means that when we take the extension of this condition, all we have to do is to shrink measure one set. We don't have to pull out. So the first operation is shrinking and the second operation is pulling out. We're not pulling out anything. We just shrink measure one set. And that's what this means. And usually, let me just say that usually this property is useful to substitute closure properties. So the forcing is obviously not closed. It's just finite condition. How could it be closed? But then if you go to this direct extension, it's kind of coarser. It's not real extension. It's real extension, but it's more strict. Then this kind of operation is close, relatively close. Depends on what the minimum element is. So this is useful. Let me just go back to this factorization, right? You factor this into a smaller part of forcing, and then the rest is a bigger part. So usually, if you remember in Eastern support iteration, the way that you show how you preserve cardinals is also to factorize the iteration into two parts. The first part has good chain condition. The second part has good closure. That's how you prove cardinals are preserved. Here, you factorize this into the first part, small, good chain condition. The second part, not really close, but close in this order. And then this fact, the Prickly lemma, is what enables you to substitute the closure of this direct extension in some of the arguments. In particular, you need this to prove that all cardinals are preserved. Okay, so I am okay. Let me just say the last few things, and I obviously talking about forcing is always not that easy in seminars. So okay, so these are the following facts. So if the length of U is less than kappa plus, so first one, then in the generic extension, the cofinality of kappa is less than kappa, it's singularized. So it depends on what so if the length is 1, then it's Prickly forcing. If the length is any successor ordinal, it's like Prickly forcing, modulo. But then if the length is, for example, omega 1, then it's going to singularize kappa to not really. Okay, there exists a condition such that below that condition, this forcing forces the cofinality of kappa is omega 1. So in any case, in such extension, if the length is less than kappa plus, then kappa is singularized. But the good thing about, okay, so why is this relevant to the study of inaccessible cardinals? And the reason is that if the length is kappa plus, then in the U, kappa is regular. This is due to Mitchell. So this is useful actually in what to see this. It takes a little bit of effort, but the way to prove this is using a strengthening of the Prickly property called the strong Prickly property to prove such a statement. But this is it's some kind of good news because there's a way of preserving, falling into the general scheme of such a forcing. Only if you change the parameter a little bit, you would be able to preserve the regularity of the cardinal in a generic extension. And if you make this a little bit longer, okay, so let me just say, if you if you make this kappa double plus, then you can have even stronger properties in the generic extension. For example, in V, in the generic extension, every stationary subset kappa reflects. This is absolute. It doesn't matter what 2 to the kappa is. I mean, if 2 to the kappa is kappa plus, then this is trivial because kappa is probably measurable inside. But then it doesn't matter what 2 to the kappa could be huge. And if this is, if the length is double plus, then it's true that every stationary subset reflects inside. And you can fine tune such theorems and so this provides a way of showing that certain compactness principle survives in a generic extension while diamond fails. So it provides a way of showing independence results. But let me just say a final thing. So the exact statement of the theorem of Woodin is that if kappa plus is less than 2 to the kappa, then, okay, and the measure sequence has length kappa plus, then in the generic extension, by this forcing, diamond fails. It's more general than that. As long, okay, let me be very general just because I want to say that it applies in this case. So if the length is less than 2 to the kappa and the cofinality of the length is greater or equal to kappa plus, then this is true. So if the length of the measure sequence is less than 2 to the kappa, and also the cofinality is greater or equal to kappa plus, this theorem Mitchell works if the cofinality of the length of the measure sequence is kappa plus. And then, so this is just to ensure that kappa remains regular in a generic extension. And the fact that you need 2 to the kappa to be greater than the length, that's what in the proof of the failure of diamond, this requires this fact. Okay, I think. Oh, and also connecting this, right? So connecting this theorem of Woodin to this particular statement, if you get 2 to the kappa to be kappa triple plus, for example, you would be able to have a situation where stationary reflection holds. Actually, something stronger holds. Some compactness principle holds, but then diamond also holds. So this is the kind of paradigm is trying to get something as compact as possible. Women diamond fails, yes. So this just means that this particular reflection principle is not strong enough to imply diamond, right? Even though, let's say such a principle is equivalent to kappa being weakly compact in L, but then in this particular model, it is not. They are equivalent L, they don't have the same consistency strength, but then in this particular model, we have stationary reflection, but it's still not strong. It's not like something being weakly compact at all to imply. I mean, I also said it last time that in such a model, in radian extension, if kappa is weakly compact, then diamond has to hold. And that's related to this nicely defined wild orders on subsets of kappa in such a model. So it's very specific to the combinatorics of this model that you can define actually a very, very easily definable well ordering some particular subsets of kappa. But again, so this is showing that there are two principles, weakly compact and every stationary subset reflex. They are both compact, but then it turns out that one thing is not as compact as the others in this model in terms of the relationship with diamond. I'm out of time. So sorry, this is harder than I expected. I mean, to talk about, but I hope it's reasonable. Thanks. Yes. Wait, what? Ah, in the rating model?
Yeah, so I guess it's just to preserve or do some access to the rating.
Yes. Yeah, weakly compact implies diamond in rating model. Yeah, yeah, you get some very nicely definable well orders of sets lying in the ground model, such that such orderings are absolute between kappa models and V. And then but then you only get those well orderings within the sets inside the ground model. So there's another extra step which I missed last time in response to a question of Elias. I lied, but so the extra step is that if you have a diamond for subsets that lie in V, then you will also get diamond for any subset. So that's something particular about this forcing. And this rating forcing has the property, if you have V diamond, only guessing subsets of V in VG, then it is also true that you guess all the subsets of kappa in VG.
The diamond you get is full then.
Yes,
Yes, you
yeah.
get
So
the
from
diamond.
V diamond, you get the full diamond. And it's very similar to the fact that Elias reminded me that if you have a diamond, that is true. And if you have a CCC forcing of size less or equal to Aleph1, it's not going to kill diamond. And the reason is just because if you have a name of a subset of Aleph1, it's essentially a subset of omega-1. So you just have to guess the name. And the reasoning here is similar, a little bit in spirit similar, but this doesn't have good chain conditions. So what are we talking about? So the similar fact here is that whenever you have a name for a subset of kappa in the rating model, then you can always find a nicer name representing the same set such that it's morally a subset of kappa. Okay. Yeah, it's related to exactly. It's related to this factorization. When you factor and you want to define in terms of this magic sequence what the initial segment of the name is, and
Raise the argument this way, can't use the rating bus to just give you the well ordering that integrates properly. Instead of taking it down.
No, we don't have to use the weak diamond. So in this situation, we can just define the well ordering directly, and the proof is not related to the first proof that I gave. It's just in spirit. You also, instead of taking in the negation of weak diamond, there's some kind of natural well order, naturally well-founded or not total order that you can use to prove diamond holes or weak diamond holes. But then in this situation, once you have a very nicely definable well ordering on certain subsets of kappa, then you can just use the same proof. Each time you collect a counterexample, but then you collect the least counterexample with respect to this ordering. And all you need is that such definition is absolute between kappa models and V. And that's. Thanks. Thanks.
So why is it that the diamond that the weekly compact is not good enough to give you a C-stage tree? What goes wrong?
Right. So if you only have